Okay, hello everyone. Good evening. So let's start today's session. So before I do that, let me share my screen. Uh, Hope my screen is visible. Okay, let's get started. Today's session will be focusing more on to some ML algorithms. Let's say support vector machines and how do boosting bagging works. Okay, so that will be the core agenda for today's session. So we'll try to understand like how these algorithm works and how do we proceed with a data given, and how do we train a model with different hyperparameter tunings with this kind of different ML algorithms. Okay, let's get started with it. So like before we go into that particular topic, I just wanted to show you a small data which is in the screen right now. So where it is basically, I have three columns where I have date, websites, and subscriptions. So basically, like it is a website where people, logs in every day. For example, your news website or maybe a movie website, like let's say Geo or Hotstar or Prime or anything. Okay, so basically they have logged how many visits have been made every day on a order starting from 1st of 2012 to the 31st of 2012. So which means that we have 31 days, which is like totally 31 data we have. For each and every data, we have website count and we have subscription rate. So subscription is something like, we basically subscribe to a particular problem. Or let's say you have Hotstar, you can watch free movies, free shows and things like that. But yes, you can also subscribe to watch some latest movies and something like that. So in that case, with this data, we are trying to create a model, for example. Okay, so we have to create insights based on this data. So basically, when you see this data, I'm not sure like how these numbers are increasing here, but basically I might have a clue that maybe this can be, a holiday or something like that. But even though when I consider that as an holiday, you can see like when I add 7 days, that doesn't make sense, because like at some intervals it is increasing high, at some it is not. But when we compare the website visits, you can very well see that whenever there is a good amount of visits, we have a good amount of subscription. So we have very limited information about this particular content. So which means that the features are there. That is your website, and your subscription rate, and the date is there. We have three features basically. With these features, obviously it will be very tough for us to create an insight. Either we have to analytically try to see like what kind of feature expansion which we can make or something like that. If at all, if you cannot create any feature expansion in this particular point, then definitely we have to go for a ML model or any algorithm that can able to sort this out. Let's say, for example, I will keep a boundary line of or it can be also a regression, but let's take in a classification scenario where I can keep a success rate would be like 10 and above. So whenever I get 10 and above subscription, that is a positive scenario. Whenever I have less than 10, I can say it as a negative scenario. Okay, so with this data, let's talk about the support vector machine. I'll just take that data as an example to make you understand how this support vector machine works. So basically, it's one of the convenient and one of the best ML algorithm which you can ever use. Now you'll be wondering, okay, what about decision trees, or what about Gaussian naive? There are many different algorithms, right? Why did I say SVMs are a little better or maybe very convenient algorithm to do it? Let's see like what it does, okay, on a higher level, and slowly we can start drilling it down to understand bit by bit. For example, what would be the hyperparameters, what are the negative scenarios, on all these things we'll cover it one by one. Okay, so basically when you have a data like this, for example, in this case you can see this is the data, right? So you have a data, and basically let's say I'm just distributing this data into class 1 and class 2. Basically this class 1 is going to be your subscription rate, I mean your positive subscription, and this is going to be your negative subscription. Okay, so this is positive and this is negative subscription. So red represents positive subscription and green represents negative subscription. So when you visualize this data, since you have only one feature, for example, you're gonna plot it against X and Y, you are kind of end up in a 2D plane. Okay, so in this particular 2D plane, we can able to see the data is kind of clustered against each other. It's not like it's kind of clustered towards each other. It's like against each other, which means that like both the data is well separated. Here you can see like this data is separated clearly and this data is also separated clearly, which clearly indicates there's a good pattern to understand here. Okay, there's a very good pattern to understand here because I have a huge gap. So what if I draw a line like this? Okay, let's take a line like this, which you can see here. So I'm just trying to draw a line and I want to design my model in a way whenever a data which is above this line, okay, whenever the data which is above this line, I will call it as positive. Whenever the data is below this line, I will call it as negative. Okay, so that's how I'm just planning to do with it. Okay, so basically I have a data with me and I'm trying to classify this data by using a singular linear line. Okay, a straight line has been created to separate these two classes. Okay, so this is the basic essence of a support vector machine. Okay, support vector machine basically tries to solve a problem by dividing the data into a planar region, or it can be a line or a planar or a multi layered or a multi-dimensional region as well. Okay, so basically that's to try to box the boundaries. Basically I try to create boundaries for each and every data. So let's say this is one boundary and this is another boundary. So whenever the data crosses above these boundaries or like beyond these boundaries, basically I'll be ending up in different class or something like that. Okay, but let's let's go a little bit deeper into it. Okay, so this is fine. I have a a decent distribution with me. That's great, and I can certainly draw a line. But you'll be wondering, is this the one line I can draw? No, right? I can certainly draw n number of lines here, right? I can draw a line. Sorry, yeah, sorry for that. So basically I can draw a line like this as well, right? And even I can draw something like this. So likewise, I can draw, n number of linear lines to separate these two data. So in that particular case, which line to choose, which line I can choose for my support vector machine. So that will be the next question which we have to keep in mind. So basically, I'm trying to separate this data, but which line to use? So that's where we are going to formulate a concept known as hard margin. Okay, a margin, a boundary which is going to be taken here. Let's say in this case, I'm going to decide the maximum gap which can be allocated for me to draw a line. What is this maximum gap? For example, this is the the outmost data for this particular class 1, and this is the outmost data for this class 2, which means that this is the true extremity data, which in between which I have some gaps where I can draw some line, which means that I'm just trying to measure this gap. Okay, and I'll try to measure this gap as well to see like which is the maximum. For example, let's take this gap can be like 1 centimeter, for example. Okay, and this is also 1 centimeter, which means that the maximum gap which I can go for is 1 centimeter each. But if it is 0.5, for example, and this is 1.5, then I have to adjust this particular margin in a way where I can able to somehow balance the two margin in a same with the same number, so that equal bias will be given for both the classes. If at all, for example, if at all I have drawing a line like this, which is in favor of class B, because I'm giving a strict margin, or I'm giving a strict gap for class 1, and I'm giving a linear margin for class 2, which means that whenever I have some data here, here, and here, okay, I will possibly say it as class 2. But even though the right data, which is red, which comes here, I'll be like, classifying it as class 2, which will be a problem because I cannot bias towards, any of the classes, because the classification should be, particularly not biased, which means that like equal priority have to be given for both the classes in respect to the distribution which I have. Yes, obviously distribution will play a huge part here, but let's say an ideal scenario where I have a good amount of data where the distribution is very clearly visible and I can able to, visually separate it with just a line, then definitely I'll go with the line that can have the maximum margin which it can bring out. For example, in this case, this is a maximum gap which I can produce to draw a line between these two classes. Okay, so this technique or this margin, we kind of call it as hard margin. Okay, we call it as hard margin. So we are kind of giving a, kind of uh, a stringent requirement here, where this is the line where you should not be crossing it. So obviously the support vector machine will try to, try to formulate multiple different lines to make sure like which should be the better fit. Because obviously in this is the ideal scenario, but in many cases you might be having very closer data like this. So in this case, identifying a margin is very, very tough. So which means that like both the data are like very closely packed against each other, which means that obviously like, the margin which is going to be like very, very minimal. So obviously I have to go with that data because I'm clearly classifying these two, data very, separately in a better way by just using this line, something like that. That's fine. Okay, this is an ideal scenario, okay, where we have a data and we are separating it by a line using hard margin. Okay. So that's the essence of it. Okay. So now let's consider the scenario, because obviously in real world situation, we have, different data distribution. Obviously, like all the data will not be this clear. If it is this clear, then we might not require an ML model at all, because, you can basically, derive everything just like that without any insights or any statistical analysis. But usually the data which you will look like this. For example, few class 2 data will be here and few class 1 data, sorry, that's too far, but yeah, that's fine. Few class class 1 data will also be here. So in this case, okay, the ideal scenario is, yes, I'm trying to draw a line that can able to separate these data. So when I draw this line, what really happens, I have four wrong results here. Okay, four false positives are here and here. So which means that like I have 5 plus 4, which is 9 wrong predictions have been created. Okay, so 9 wrong predictions, which means that no matter like how much I try, for example, if I try to draw a line which is something like this, then obviously I'll be missing out these two data which is entering here, which is again going to create more chaos. Instead of handling this one data towards this guy, I'm losing the integrity of my SVM model the first place. So in this particular case, obviously hard margin cannot create a better model with with a variation in a data, so which is highly which has a high variance in it. Obviously it is very tough for the model to understand more about this, because it's like a 2D scenario here. I'm trying to the maximum to understand like how do I draw a line, but here the scenario is totally like impossible here, because I can never draw a single line that can able to classify this data unless and until okay, unless and until if I let me take few lines, for example, let's take few red dots here and few green dots here. Okay, so as I told you, it is impossible to draw a line unless and until I can go with the linear, or sorry, a polynomial degree line. For example, where in this case the line would be looking something like this. So in this case, I have clearly created a boundary, but even though in that particular case, I have some red data here. So maybe I have to, iterate this data in a way where all these red, has been considered something like this. You can clearly see here. Okay, I can even draw a line where it can, passes this green out of the boundary or something like that. But yes, in this case, I have dealt with a non-linear line that can able to classify all the data points. But yes, only one error has been created. So only one error is there, which is really good. But the problem is this particular nonlinear data, or this particular nonlinear, boundaries which has been drawn is kind of biased, I would say, because the data are very closely aligned. What if I get a new data during my prediction? What if I get a new data which is here? This will obviously treat it as green, but instead it should be class 1. So which means that sometimes there is two possibilities. One is like it will be too much of complexity to draw this kind of a non-linear line to classify all your data, and the second would be like the model will be too much biased with the data, which means that like it's kind of overfitting with the current given data. So when overfit happens, obviously the model stops learning and focus more into the training data, and instead of generalizing the content. So this is a hard pass scenario. So how did support vector machine tackle this scenario? Because I was clearly mentioning you that support vector machine is one of the clear winner, or a best model which you can never use, which means like how did they handle this problem? So basically what they did is okay, they created another concept known as soft margin. Okay, they created another concept known as soft margin. So what is soft margin? For example, as I told you, if I have some, some data like this, okay, some opposite data, which the hard margin cannot separate, I use this soft margin and I try to, penalize this wrong prediction with an error. Okay. So basically this is E1. Okay. And similarly, this would be like, E2, this would be E3, and this would be E4. So I have created 4 error values or 4 error rates, which is going to be my penalizing factor. So basically, whatever data which is not falling towards a hard margin, I have to try to penalize this data so that the model will try to bend its line to a better way. Okay, so that's the the idealistic or the idea behind this soft margin. So basically, when you see in terms of as an expression, so basically the idea of this margin, or the idea of the gap, is to bigger the gap, better the model, correct? Because the larger the gap it creates, the better the model can able to function, which means that obviously the model is going to give a very good accuracy. So on a contrary, I would say 1 by gap is what we require, correct? So minimum of 1 by gap. So if I'm like inversing it, I can say it as minimum of 1 by gap. Okay, maybe let me like write it in a separate place where you can able to understand a little better. So basically I'm trying to summarize here. So bigger the gap, okay, better the model performance. Okay, now if I create it on another contradictory, I would say 1 by gap, inverse of gap, which means that like minimum of this inversion gap, which leads to a better model again, which is a good model. So now, since I'm introducing the soft margin into consideration, so I can rewrite this equation as minimum of 1 by gap multiplied by summation of all the errors. Okay, so by summation of n is equal to 0 to infinity and value of n. So whenever I find all these non classify, or let's say wrongly classified data with respect to the hard margin, I kind of create this value. This error can also be termed as loss or anything, or it can be also termed as penalty or anything. Okay, so you can keep your fancy naming to it, but basically I'm just trying to add some more values, which is going to be like I mean, destroying this gap, because obviously like when this value increases, the minimality will not be there, because it's going to increase. The more, let's say for example, this E, the summation of E gives you 10 and the gap is 5, then obviously you're going to have 2. But I have to go as minimal as possible to 0, which means that 2 is a very big number to me. So in this case, I try to reduce this error and I try to maximize my gap so that I can able to create a better support vector machine model. So this particular formula, it is very familiar, I would say. This is called hinge loss. Okay, so people even call it as hinge loss. Okay, so which is very famous in many situations, because basically you're trying to solve a problem based on a loss. Okay, so here this loss is considering two things. One is the hard margin Another one is the soft margin. Okay, so soft margin really plays a vital role here, because soft margin makes the model to understand like where it went wrong, how much deviation does the hard margin have. So based on this this penalty, the the model tries to evolve from that particular point of time. But there is one more catch to it. So you'll be wondering, okay, even though I kind of increase my penalty, and I try to use the hinge loss to to reduce it as much as possible, whether a linear line can be very effective in this case. Yes, obviously linear line cannot be very effective in many situations. Sometimes in SVM we can even support multiple different kernels. Okay, kernels like you know uh, polynomial kernel, linear, that, and we also have this RBF, and we also have the sigmoid. Sigmoid is something like a, we can talk about the sigmoid a little later when we enter into, neural network standpoint. But basically, linear is like a degree one, right? Polynomial has multi degrees, which means that, like, you can go with degree 3 or degree 4 or degree 5, making sure like, you get all the bends you get, making sure the model is kind of generalized in a way. RBF is like, radial based filter, which, consider drawing a line based on the radiality. For example, it draws a circle based on the particular given point, and it tries to see like where are the data present. Based on that, the point traverse, slowly, like the next point of travel, it will draw another radius. Likewise, it will create a radial based search filtering to make sure the lines are created very properly. So basically, support vector machine tries to divide the data features in a way where it can be able to classify. Obviously, in many cases linearity will not be very helpful or functional. In many cases, in that case, you can very well use a soft margin to bend the line in a way where it can be able to adapt to the given data. Because as I told you, whenever the loss is happening, the line will not be very fluctuating. It will, slowly it will start fluctuate, something like this. Not like it goes here and go inside this particular data and comes like this is very too much, too much of flexibility given. So when I give too much of flexibility, that's going to be another big problem. So I'll make sure the soft margin which I've given is going to be like not exaggerated much. But sometimes, yes, I can also exaggerate this loss as well. For example, the formula, right? So which is x summation of the error rates divided by the gap, correct? So what if I square it? What if I square this error rate, which means that I'm going to penalize it even more? For example, this is just an ideology which I'm trying to say. Okay, so there are many different ways to create your own support vector machine, but you have to change few things inside the code, as in the base code as well. So in this case, you can see, what if I exaggerate my penalty little bit to make sure whether if at all it creates a better classification. So that's in that way I can able to clearly exaggerate it by squaring it up. Now you'll be wondering, what if I square this as well? Squaring this and not squaring this will not really help, because soft margin plays a vital role than the hard margin, because hard margin is one single approximation line, but after that how much it has to bend, or how much it has to go in a radial fashion, or a polynomial fashion, this error rate decides. So if I square this up and not square this error rate, what really happens? This gap, or this hard margin overpowers this soft margin, which means that the line will not evolve at all. But yes, maybe there can be some areas where this can also be useful, but I don't see a particular use case here. But in many situations, if you want to penalize more, I can certainly square up my error rates in a better manner. Okay, so instead of squaring the gap. Or maybe another case would be like taking a square root of this gap. Yeah, obviously, like inversely, instead of squaring this guy, I'm going to like take an inverse of this gap. So both cases works well and good. If at all you want to like improvise on this support vector machine as such as it is. Okay, so this is one ideology behind support vector machine. So whenever you have a data, or let's say a feature, we try to classify the boundaries of it. Is it clear? Any doubts or clarification at this point? Okay, so sounds good. Since I guess like there's no relevant questions for it. Okay, so now But anyways, this is just an ideal scenario. Again, as I told you, we have a data with us, right? So that data has only one or two features behind it. Uh, yes, I'll just give a very short ideology for this topic because someone has asked for it. So basically, like you can see here, I'm trying to classify this data by drawing a line. Okay, so I have some distributions here and here. Okay, so it's basically taken from a features. Let's take this feature. So I have some website subscriptions versus the website visits. Based on that, I'm just trying to create a two-dimensional map of the data, and I'm trying to draw a line that can able to classify these two data. So basically drawing a line like this is a hard margin that can never be correct, because obviously it's going to be very tough, because many times the distribution of data is not very ideal like this. We might have a lot of data here and here, like class 2 data will be here and class 1 data can also be here. So in that case, I can never draw a line which is very straight. I have to bend this line. But how do I bend it? I should not be bending this line too much, so that it leads to overfitting. So that's where I create this soft margin, where I kind of penalize each and every data which is off from the actual line, which is called as soft margin. So basically the formula would be like summation of all the soft margin, which is going to be in the form of an error rate or a loss or a penalty, divided by the gap. So bigger the gap, inverse it is going to be like very beneficial to me, and more lesser the error rate will create lesser value. So minimum of it will achieve a better model. So this is particularly called as hinge loss. Hinge loss will be like used is kind of utilized here argumentatively. It has been used here. So this is called support vector machine, but this is very ideal. Okay, since I have only two features with me, I easily put place it onto a two-dimensional plane, and I try to draw a line. That is very, very simple and ideal in this case. Okay, so with this particular data in mind, let me give you few more informations. For example, I guess like once you try to solve different problems or different data which is given, definitely like we'll be having a lot of different features, because it's not like only one feature will be there. Obviously there can be many features. For example, if you are going to do some face recognition, or even using creating a chatbot or something like that, you might be ending up with more number of features. So more the feature, it will be it will be tough for my support vector machine, correct? Because you see, in this ideal scenario, I can able to draw a single line that can able to classify these two features. That's all. But what if I have multi features, like let's say 10, 20, 30? How does our support vector machine handle this multi-feature? That's one of the problem. And the next thing would be like, okay, this works for a binary class, right? Because this is class 1 and class 2. What if I have another class named class 3, which is distributed here, in between, or maybe at this particular region? So how does support vector machine create multiple different lines for multi-class problem? So how does multi-feature and multi-class being handled by support vector machine? That's what we're going to see right now. But basically, when they created the support vector machine, they try to solve a binary class problem with that has a binary feature. Okay, so they didn't thought this through, because the nature of this support vector machine solves by comparing two features or two data on a contact array. But they kind of utilize the same ideology to to manage this flaw, where let's take this particular data. For example, you have this kind of a data. Okay, so you have you have this particular data with you, where it is very clear that I have one class which is green and another class which is orange. I have some distribution like this. Either I can use a polynomial degree data. For example, I try to draw or create a support vector machine model that can able to draw a boundary like this. Okay, but this is very, very tough, because creating a circle, it's not that easy, because basically support vector machine starts with a line, or start from this point. Okay, start at this point, slowly try to boundary. slowly try to find the boundary which is correctly classify these two data in a given case. So in this case, I don't have multiple features, but let's say I have only two features. That's fine. But in this case, when I have two features also, sometimes this kind of non-linear decision boundary is very, very tough, obviously, because of the case. The complexity here you can see where you cannot clearly classify this data in terms of a singular polynomial line or something. It's going to be very tough to create this kind of a circle just like that with your support vector machine, because it has to slowly evolve, because you might be ending up with a very big penalty, because when you try to draw a hard margin, definitely the penalty will be like too high. So slowly the model has to evolve this particular point. So that's where we try to enlarge the feature, okay, enhance the feature by using this third feature representation here. For example, what I did is, let's take this x1 and x2, right? So I have x1 x2 here. Okay, on a third dimension, I kind of constructed this data based on the distance from the center point. Okay, for example, this is my center point. Based on this distance from the center point, I take that distance as x3. Okay, I enlarge my feature, okay, where I can able to create it as a three-dimensional feature map here. Now it is very clear that, okay, so whenever I take the distance from the center, you can very well see here, okay, the green dots, which is very, very close to the center pointer, which means that all the green dots will settle at the bottom, correct? And all the orange or the or the other feature or for the other class, it will be like settling in the topper or the upper space of this x3, which means that when you visualize this data in a three-dimensional space by increasing the feature map, okay, or by increasing the number of features, definitely it will help us to classify any problem. But in this case, you can see, how do I draw a line to classify this three-dimensional data using support vector machine? That's not possible, right? So that's where we go with the planar planar value. Planar value, since I try to draw a particular plane which is two-dimensional in nature, and try to classify this data instead of drawing a line, because it's for a two-dimensional space. I draw a line. One-dimensional line is enough for me to classify it. If it is a three-dimensional space, I draw a 2D plane to classify it. What if it is a four-dimensional space? I try to draw a three-dimensional cube or a three-dimensional an object to classify. Likewise, more the dimensions, more my planar dimension will also increase to classify the given data. Okay, this is all about your multi-feature. So more the features, more the dimension it will be. So more the dimensions, it will create a a different polygonal dimensional line with hard and soft margin into consideration. It will try to draw a way where it can able to encapsulate the data. And again, for this multi-feature as well, I am focusing on to a binary class problem, which means that you have only two classes, class A and class B. Okay, so for class A and class B, even though you have multiple features to consider, yes, I can definitely go with the support vector machine, because I can able to create a n-dimensional plane to classify the given data. Okay, so that's one thing. Yep. Sure. So yeah, we'll do that. And okay, so that's one particular thing. Okay, so now let's go for the second problem, okay, where you have this multi-class problem. So as the nature, you can see support vector machine clearly states it can able to separate two data only, which means that it can able to classify A or B, which is a binary problem. So in order to enlarge this particular support vector machine for a multi-class problem, okay, I certainly try to utilize two strategies here. One is one versus one, okay, another is one versus rest. So what is one versus one? For example, if I have four classes, which means that I'll go with a round robin. Let's take the four classes to be A, B, C, and D. So what I'll do is I'll try to create a support vector machine for A of A and B, and I'll go with B and C, and I'll go with C and D. And finally, it's going to be D versus A. So I'll be having four combinations here where all the data have been have been competed against each other. So where I try to draw a boundary for A and B, where and in the second case, I try to draw a boundary between B and C. Similarly, the next case, it's going to be C and D, and next is going to be D and A. So where all the pairs have been combined. So for example, in this case, let's take this A and B. Okay. So when I try to create a support vector machine for this A and B data alone, I don't consider or I don't mind about this class C or class D at all. because it is very clear that I'm just focusing on these two data, which means that, for example, in this case, let's take this is class A and this is class B, for example. In this case, I draw this blue line, okay, that focus only on this class A and class B. I don't mind, or I don't, usually don't see where the red data is, because I don't want that, because I'm totally focusing on these two data. Likewise, whenever this one-to-one approach is used, I focus on one-to-one data. Okay, but it has been proven that, okay, on a broad view, on a overall view, okay, the model might not be doing a very good job here, because you can very well see here, like whenever I draw a distribution, it might even intersect with class C, or multiple classes as well. So one versus one is not very successful in nature, but yes, at some point of time, or in some very minor cases, this one versus one can be little useful. But predominantly, and also as a default method, people always use one versus test. So what this one versus test is all about? For example, let's take three classes here. Okay, let us E, A, B, and C. So in the first case, what I will do is I'll take A as one class and the remaining classes as a rest. Okay, so class B and class C consider as one single class. Okay, I'm gonna let's take, this is A, and this is B, and this is C, which means that like when I try to construct this green line, I consider this and this as one single data. So now this green line is more aware and more focused on not touching this class C and class B, but making sure it can able to classify A versus BC. The next combination would be, taking B and having A and C into consideration, which means that like this line. So in this case, A and C will be taken as one single class and B will be taken as one class. So in this case, this blue is clearly stating that I can able to use this line where I am just classifying B against A and C. And similarly, I can go with C versus AB, right? So C versus AB, where I draw this line. So using this one versus rest approach, I can clearly state where my margins can be created. So yes, obviously I will be ending up with three lines. Obviously, like whenever the data distribution falls in this area, I can say this class A, this is class B, and class C. Very simple. But in this case, it's too complex here because I have, many number of combinations. And again, you can see like the cons of this one versus one is like, it is very expensive, which means that like I have to do multiple combinations. Let's say if I have three classes, I will have three combinations. If I have four classes, I will have four combinations. Five. So it's going to increase based on the number of class increases. Obviously, one versus test will also increase, but the combination will somehow reduce because number of class is equal to number of iteration. But in this case, it's going to increase exponentially as we see. So, and also on another note, on a precision wise, one versus rest will always work a little better than the one versus one in many scenarios. But yes, we cannot assume that every time only when I use this one versus rest, every time this will work. It's not like that because it is entirely dependent on the data you use. Sometimes the data can be really aligned towards this one versus rest, but sometimes the data which you have might work a little better when you use this one versus one strategy. So you can never say this is the best setting which will work for every data which you get. It's not like that, because there are a lot of data which is available. There are numerical data and natural language processing. That's your GPT models, and many different data are there, like images, sound, or many different models are there which is available. So which means that I can never possibly satisfy a particular setting that can be commonly used for all the data. It's not like that. You have to hyper parameterize and see like which gives you the better results. Okay, so let's take another scenario here. So as I told you, as I was, this is one continuity which I missed here. So coming back to this multi-feature problem. Okay, so as I told you, like in this case, you have this, X3, which I'm enlarging by, creating a center point and find the distance between it. Similarly, for the first data which we have saw here, right, where I have website visit and subscription, we had a hunch that what if it is a holiday and I have more subscription and more visits. So I kind of visualize this data here, and you can very well see here, during Friday, Saturday, and Sunday, I have more subscriptions, obviously, because of the fact, obviously, holiday means, you kind of visit the entertainment website or something like that, and you kind of subscribe to it to watch some movies or something like that. So which means that when I add more features or, enlarge my feature capacity, I end up with having a very simpler and a better model, because this is very evident here, because instead of me drawing a circle like this, I can enlarge it like it, so that I can able to create a planar, two-dimensional plane where I can able to, split the data very conveniently and very clearly. Okay, so this is all about multi-feature based SVMs, but it's not only, common. It's not only particular for SVMs. It's not like that. You can utilize this multi-feature technique, enhancing your features technique in a way where the model can. So it can be applied for any models. Okay, it can be machine learning, it can be neural network, it can be anything. The more insights you bring, okay, the more insights you bring to a data, it will be easier for the model to understand. Okay, so once I give this another insight, like let's say the day the calendar date to my, when I add this calendar date to my data set, it is even more easier for my model to, understand, because even now we can able to understand this data a little better than just seeing that particular, tables just like that. Right, the numbers doesn't make sense, but when you like graphically see based on the days, and when I like, go even more deeper by, adding this holidays, whether it is a Friday holiday or a Sunday holiday. Sometimes, you get a chain holidays, Friday to Monday. So in those cases, like how the behavior is. So those kind of trends I can able to easily, create when I enhance the features. More the features, better the model understanding would be, which is common for any model creation. I hope this is clear. Any doubts or clarification? Yeah. So basically, this is a classification problem. Okay, so it can be used for any problem. For example, you have let's say a review system. Okay, so in your in any platforms, let's say Amazon or Flipkart, something like that, you have different products and you have a lot of reviews, right? So you kind of not sure like which is the right review. I mean, how many have given a positive review and how many have given a negative review, because sometimes people put 1-star rating and they give a good positive feedback. They would be understanding it in a way where 1 means first and 5 means last. So something like that, no, like this kind of problem will happen. So like, how do I utilize this text in a way where I can able to classify a positive versus negative review? So in that case, I can, collect data. For example, I can collect some 1,000, comments for a product, and I, manually label it. Let's say this is the positive review and this is a negative review. I split the data and I extract some features out of it, and I train a model. During the training process, I can use this SVM to classify these two data. And basically, once I classify, learns it, whenever I give a new input data, for example, a new review comes in, I can very well say it is a positive review or a negative review. So likewise, you have many situations like face recognition, your all the AI model, which is supervised in nature, works with this classification problem. Okay, so most of the problems comes with classification, objection, or many cases are there, but this is the basic essence of it. Okay, so we are trying to create a, no, it's not like it's useful only for rating, as I told you. Okay, it can be used in many different ways. Let's say you have a brain tumor classification. Okay, you have multiple CT scans or MRIs. So you can take that data, you can extract some features out of it, and you can push that complex data. But what I'm talking about is, based out of images, which means that images will have more pixels or more features within it. So more the features, the complex the model will become. That's fine, because my support vector machine can able to handle multiple features very easily, which means that I can clearly use support vector machine to handle a complex problem. So let me, maybe I'll just give you another a simple scenario. Okay, so let's take a scenario where an HR is there and he has to create a function to, to select and reject a candidate based on a resume. Okay, so the HR starts to create some, rules for it. For example, the mark should be something like this. You should have a good percentage, and you should have done number of projects. You should have done, multiple publications, and you should have good experience in this particular technology, and blah blah blah, and something like that. But even though when you do that, the more screening you do, the better, the better processing which you can get. But let's say if you screen only with the marks, then you might be missing out good talents, because some might have a good talent, good experience in the technology which you're looking for, which is not criterized for the current search. Likewise, the more features you drill down from the resume, the better understanding you get from the, of a particular candidate. So even though when you have more data, okay, and you have 100 of candidates to go with, I use a simple algorithm like the support vector machine or something like that to classify which are the top top priority candidates, which is the second top priority or the third top priority candidate. So likewise, I can segregate it. So every classification can be done using this support vector machine. It can be anything, positive or negative, phase A versus phase B, or your even your face unlock system, which is in your mobile phone, right? So only it unlocks for your face, which means that you have created, images of your face, and the rest of the face will be considered as class B, and your face alone will be considered as class A when you use a support vector machine. Likewise, it's not like only support vector machine can be utilized. There are multiple different algorithms, which we'll be discussing in the upcoming slides. I hope this is very clear. Do we have any doubts or clarification at this point? Yes. Okay. So since there are no doubts or clarification, I'll just walk you towards a particular data where I'm trying to classify the particular data using a simple program. Okay, so let me open that. Give me a second. Sharing it again. Yeah, so I'll just show you the coding part of the support vector machine. Okay, before we go to this coding part, let me show you the data set which we're going to use here. Okay, so here I've used different data, okay, where it has multiple features, but it has only binary class, it is 0 and 1. So this last column represents whether it is class A or class B. So 1 represents class B and 0 represents class A. So I have like 3, 4, 5, 6, 7, 8 features, okay, which is like 8 different parameters which I've used for the model training. So what are these parameters? Okay, I'll just give you a small insight about this data. Okay, so this data set is called as PIMA Indian diabetes data set, which is something like a phenomenon which will happen during pregnancy. Okay, so during the time of pregnancy, a gestation diabetes will happen. So there's a possibility for the women, okay, during the time of pregnancy, they might get this diabetes. Okay, so this diabetes is a temporary one, but it happens during the time of pregnancy. So in that case, I've just taken few parameters, like let's say like number of time pregnant, and blood pressure, like systolic and diastolic, and body mass index, and few more parameters like that. Okay, so like insulin level and all those things. And finally, I also have the age. So age is there, number of time pregnant is there, BP, body mass index, and some insulin, challenge level is there, which is kind of collected from a test. Okay, so from a test, they have collected these many, like 8 features or 8 parameters for a given patient, and we have a data close to 768 entries, which means that I have 768 data with me that has a span between 1 or 0, which means that 0 represents non-diabetic, 1 represents diabetic. Okay, so that's a plan. Okay, so basically, when you see this data, I can somehow try to create a logical map between these two guys. For example, I have number of time pregnant, and let's take this age into consideration. For example, okay, so in this case, whenever the age is above 31, okay, I can see there is a good chance of having number 1. For example, in this case, for 50, I have diabetes. For 31, I don't have diabetes. For 32, I have diabetes. 21, I don't have. 33, I do have. 30, again, I don't have. But again, till the 6 data, I was little confident that whenever the age is above 32, the patient might have diabetes. But that's totally wrong, because you can see that even at the age of 26, I have people had diabetes. And sometimes age of 57, a patient who was age of 57 doesn't have diabetes. And now, okay, so obviously this one single feature will not be helping me. So that's where I kind of combine all these features together to form a decisive, a combined decision, because obviously like all these features will contribute to my learning. Okay, so now let's utilize this data and try to see like how my support vector machine helped me to classify this data. And one more heads up, okay, this particular data is not that easy, okay, because the number of data which I have is very, very less. Because lesser the data, okay, lesser the data, complex the model will become, because it is having very, very less distribution. It is something like, let's say, if you have given, like, let's say 10 days of time to study a subject, how you will perform. And what if you were given 10 months to study the same subject? Obviously, if you are studying the same subject for 10 months, you will become an expert. Or if you're doing a job for 10 days and you're doing the same job for 10 months, obviously you'll be becoming more and more better and better in that particular job, which means that more the experience or more the data, better my generalization will become, more understanding will be there. So in this case, I have 760 data. Now you'll be wondering, like, okay, I have 760 data. Isn't that enough? Yes, it can be enough, but it is a problem of distribution, because sometimes the distribution, the data which you have is not really sufficient, because during some situation where the woman gets a lot of stress, okay, for example, if they have more stress, then there's a good possibility of getting diabetes. So those kind of data are not collected, and their genes, or let's say that does their mother have diabetes, something like this. So there are many other logical parameters that's not linked here, which means that you have very less number of features to utilize, and you have very less entries to deal with. So in that case, I'm trying to utilize this data and try to train a model here. Okay, so for that, I'm just using some necessary imports. Okay, basically I'm using this scikit-learn support vector machine here, which is very clearly shown in this line number 4. Remaining are just for my just for the betterment of loading the data. So basically I'm using this numpy. Okay, I'm using this numpy library to load my data set, okay, which is in the form of CSV file, which I showed you now. CSV, as the name implies, is a comma separated value. So I'm going to use this delimiter as comma, so that all the data which is going to be collected using this numpy will be stored as a matrix, which means that, like, the matrix will look something like this, where I have all the features and all the rows entries sorted out. So basically, once the data set is loaded, I have to separate this data into input and output, which means that I need to know, because I have to give what's the input and what's output. So in that case, I'm going to take using a split method, slicing method. I guess you are saw this slicing method for one-dimensional data, but let's take this two-dimensional. The first parameter represents the rows, and the second parameter represents the column, which means that since I'm giving empty, all the rows will be considered, because I need to have all the data with me. And in this case, I will be considering the first 7 rows, which means, sorry, the first 8 rows, starting from 0 to 7, exclusive of 8, which means that I'm going to take the first 8 rows from 0 to 8. That's going to be my input. What about the label? I also have to go with all the rows, but only the 9th column. Typically, since it is 0 index, it's going to point towards the 9th column. So the first 8 columns have been like splitted and taken as input, and the last column has been splitted and taken as an out. Okay. Now, since I got this data set, I'm going to split the data set furthermore. Why do I need a split? Obviously, I guess you would have learned about this splitting technique, because obviously when you are training a model, you should have a separate test set which is not exposed to the model, because it's like keeping an examination to you to understand like how better you are. Okay, you are studying a subject and I want to know more about like how you have done. I'll be giving some programs or problems which is not in the book. So obviously you will not be like by hearting it. So I should want to see how conceptually I've learned it. So in that case, I'm gonna split the data into training and testing. So okay, train data and train labels will be useless for my training. Test data and test labels will be used for my testing. Okay, so now I'm introducing the support vector machine function. I'm giving a random state as 42. What is this random state again? Basically, when you have this data, okay, so I have this some 768 data, right? So when I have this 768 data, obviously, like, I'll be like, I should not be loading the data in a row, in an orderly fashion. It should be like totally random, so that the distribution is there in a better way. So in that case, if I go with a random distribution, everyone who's going to run the program might be ending up with different results. Because if you have first 10 data is very good, then sometimes the model will evolve really great. But sometimes when the first 10 data is not really great, the model will not evolve. So which means that I have to give a bias to my randomness. So there'll be randomness, but it is kind of biased in a way so that everyone who's going to run this particular program, okay, will get the same results. And I'm using another parameter known as C is equal to 1. Yeah, so there's one more thing to it. So I'll just teach you what is C. Let's go to the slide. So When I give a C, a value named C, C is nothing but a sensitivity factor. Okay, lesser the value, okay, lesser the C value, the C the value, it will be more sensitive, which means that it kind of goes and create a margin which is very very close to the data. Okay, lesser the data, more sensitive to the given data, which means that like it can also form some intermediary boundary like this. Okay, let's say this boundary or maybe something like this, which means that more the C value, lesser the sensitivity, lesser the C value, more the sensitivity. So it will give more importance to the data, which means that it can also leads to overfitting as well. When your data is closely packed, okay, in this case, it's not very closely packed. When your data is very closely packed, in that case, you can use this, very, very, very small C value. But in this case, I'm going to go with C is equal to 1, which is the default thing. Okay. And I'm also like, taking the time, noting down the time required to train the model to see like how much time does it take to train the model. And I'm going to like, print the training score and the testing score. Also, I'm going to like give you a report as well. This is like a form of a report where I can even get more of such details. And using that particular report or using this particular testing data and the predictions out of it, I can also create a confusion matrix. Okay, I'll just run this code. You'll get to know like what it really does. Okay, so I'm just gonna put my command prompt. So I'm just running the SVM with the given data. I'll just go step by step here. So now you can see this is the time taken for me to train my model, which is like very very less. That's very good. And you can see my training accuracy is 77% and my testing accuracy is 73. So which is clearly stating that the model is not overfitting, but it is it is not evolving. Okay, it is kind of stagnated between 70 to 80%. So the maximum it can get is only 77, or the maximum learnability is very less. It's kind of a average down to 73%. Okay, based on the test data, because we only have to measure the performance only with the test data only. But this doesn't give more details, right? Because it has only a number which is common for all the classes. How do we understand more about the classes itself? Because sometimes class 0 can be really good, or class 1 can be really good. For that, we are going to like use this classification report where you get more information about it. Okay, for example, how does the class 1 performs and how does this class 2 perform? So in this case, you can see I have a metrics known as precision, recall, and FN score, and I do also have a support. So I'll just teach you what is precision, recall, FN score. Okay, so I cannot repeat support vector again. You can watch the video after. Yes. So in this case, precision is something like I'll just put it in a very simple term. The basic formula for precision is like true positive plus false positive by true positive. Okay, this is for precision. And for recall, this is true positive plus false negative divided by true positive, which means that when I have too much of false positive nature in my data, false positive, it's like wrongly predicting. Instead of A, it is saying it as B. Okay, it is not missing the data, but it is saying something. Like this is B or this is C. Something. Instead of saying it as A, it is saying it as B, which means that when you have more false positive, your precision will decrease. And when you're missing the data completely, I'm just saying it is not A or it is not B. In that case, your recall will decrease. So when you have a good precision and recall altogether, which means that you have a better model. So that's one thing you can keep. So the average of precision recall is kind of measured in terms of FN score. So FN score will give you the right, measure as well. It's like averaging this two things together. It's like 2 into 2 positive plus false positive by true positive plus true negative, something like that. Okay, so which is a combination of both precision and recall together. Or you can even create a different formula like 2 into precision plus recall by precision into recall, something like that. But anyways, this is on a simply put, I'm just taking an average of these two guys. Okay, so I'm just taking an average, cumulative average of these two guys and getting this F1 score. What is support represents? Support is something like I've used 123 data. Okay, I've used 123 data to get these numbers. Okay, so only 120 data testing data has been utilized for this prediction, and I've got these many numbers. And when you go with this class 1, you can see the precision is good, which means there is very less false positive, but many things has been left out. Instead of class 1, it is saying as class 0, which means you can see like very clearly see like the recall is very, very bad. So I'm getting a very, very low FN score, which is clearly stating that I have an imbalance in my data, because you can see out of 192 test data which I've used, there's like, twice the amount of class 0 than class 1. So I have less data for class 1 and more data for class 0, which is also a problem, I would say. But class 1 is not performing really, really good in this case. So either I have to, tune my hyperparameters in a way, or I have to try to, see for some better data. Similarly, I can also get this confusion matrix where I can, consider against, for example, this is like, more the numbers in the diagonal are better, which means that like 106 has been correctly predicted for class 0 and 34 has been correctly predicted as class 1. But 35 classes or 35 images have been wrongly predicted as no, instead it should be yes. And similarly, it is like, vice versa to it. Because which means that like more the numbers when you see it in a diagonal fashion, better the model is. Okay, so there are multiple ways to analyze the model. Okay, so this is one way of doing it, using confusion metrics or using, pressure recall FN score. There are many different methods to do it, but this is one simpler way to proceed with. Now, let me, tune the hyperparameter. Okay, so what I will do, let's take, C is equal to 0.1. Okay, I'll try to run this now. Obviously, when I use, a smaller C, there should be some, some increase in my training time as well. But you can see it's very negligible because like it's going in microseconds. So, sorry, in milliseconds. So I don't mind. Now let's see the results. What happened here? So I'm getting an FN score of 65, an accuracy of 65, which is very less than the previous one. But you can see there's a clear increase in recall alone for class 0, but everything got reduced, which means that the data is not too sensitive in a way. So what I can do, I'll try to, increase the C value to be 2. Likewise, I have to, evolve my hyperparameters to understand like more about the data. So in this case, I have 74, which is better than the 73, right? Because now you can see my class 1 is also somehow improved from 57 to 61, which is really good. So likewise, I can, hyperparameters, like I can also use this kernel as RBF. Sorry, RBF is kind of the default kernel which has been utilized. I can even, change it as linear. Let's see like how linear works. I guess when I use linear, C should not be used, but let's see like how it goes. Yeah, it is being handled inside. That's good. Let's see like what happens here. The precision, the overall accuracy kind of stayed, but it's not even doing a very significant impact. But I would stick with RBF because RBF is the default one. Well, its default is a little better, but sometimes you can evolve, on top of that as well. Okay, but nevertheless, one interesting fact about this particular data. Okay, here I can see. You can see here like this is 63 and this is 79. For the best performing model, okay, the accuracy is 74, but for class 1, it is 61. But in this case, it is 63, which is giving more balance towards my model understanding, which means that maybe I can also utilize this data or this model because I even have a balance metric, even though the number is little less, I don't mind because I have a balancing, I kind of have a balance here. So that likewise, I can evolve using these hyperparameters. I can evolve very much, using different methods. So you can very well go to scikit-learn website. Okay, so for example, scikit-learn, I just type scikit-learn SVM. You get all the parameters. Okay, there are different parameters is available. You can see like there is kernel, degree, gamma, coefficient, shrinking, probability, tall. There are many different sizes. Okay, so class weight is also there. If I want to give more weightage to class 1 or class 0, I can also do that. Likewise, all the informations and detailed information will be given inside here. So if you want to trying to do different functions, you can very well use it. So you can see this is the distance function set, which is like 1 versus 1 and 1 versus rest, which I told you, right? So default is 1 versus rest. I can also use distance function shape to be OVO also. So if required. and class weight. You can see multiple parameters C for each class computed based on the class weight parameter. So I can, give the number of classes. I can, try all these parameters and see like how it works. But basically, C and kernels are two important hyperparameters which people use. Apart from that, you have this auto scale gamma. Gamma is also very sensitive to boundaries. The whatever boundary which you're going to draw is going to be can be sensitized based on this gamma value. Similar to C, gamma is sensitive factor for the boundary, whereas the C is sensitive to the data itself. Okay, so this is how you can able to create your own program for any given numerical data using support vector machine. But consider this is just a data. Okay, so if you have multiple different data, you can utilize the same methodology using support vector machine. Let's say you have images, you have text, you have sound, you have anything. All you have to do is try to extract some features. Okay, try to extract some features and try to generate the different features for given data and give a class to it so that you can able to train a model using any ML model. Okay, so that's one thing about support vector machine. Hope this is clear. Any doubts or clarification at this point? Okay, so hope support vector machines are clear. So you can very well refer to this code if required. Okay, but you can get more of such examples even with scikit-learn's official repository as well, because they have also given more examples here. Okay, you can see like they would have created some dummy data like X and Y, and then they try to train a model or something like that. So basically, like once you get the model as X and Y, everything will be like pretty straightforward. Okay, so I would say like till this you might have some struggle for different data. So once you generate this data, it's a matter of a function call. The function call will give you the results of such. Okay, that's one thing about support vector machine. And obviously scikit-learn is a very useful library where all these ML models or these classical ML models are there, easily derived, for us to utilize it just like that under the hood. Even though you don't know much about the algorithm, you can very well, call the functions and see like how it works. If it works good, then see like what are the parameters. If you don't know the parameters, understand like what does it do, so that you will gain more attention on top of it. It's like, a practical based learning, which you can also, incorporate when you train your models. Okay, this is the first topic which I wanted to cover. Hope there are no doubts or clarifications. Okay, so since there is no doubts or clarifications, let's move to the next topic. Sorry. Yeah, the next topic named ensampling. Okay, ensampling is another, a different technique which people always utilize to increase the efficiency of the model. So what is ensampling in the first place? Basically, when I have a training data with me, when I have a data with me and I have a model, okay, if the model is not performing really good, what can I do? Obviously, I can, as you saw, I, created different hyperparameters I trained, and I ended up increasing the accuracy from 73 to 74. Just 1% has been increased. That's not a very substantial increase, right? So what else I can do to make my model become better? If at all your training data is very limited, because let's say you cannot collect more data out of it, that's the requirement, because sometimes customers and sometimes the data set which you have will not have more data, so there can be some limitation. So when in that particular case, how do I train a model that can evolve better? Just like that. So that's where this ensampling comes into play, where I create different models. Okay, I create different models with the same data, and each and every model will be evolving at its own pattern. So I can use that model and aggregate all the predictions done for the same data, and I take a combined decision. It is like taking a poll, or your very own election system, right? So you have two parties, or you might have 10 parties. It's not like one guy is going to decide the entire fate of India. So all the people in India will vote, will see like which party do I want to make sure he's ruling. So based on the majority of votes, that particular ruling party will comes into play, which means it's not a singular decision, it's like a collective. The more the model marry, the problem will be solved, which means that like ensembling is a technique where I create different models for the same data, so that each and every model can able to, give a different insight. Using that insight, I can, aggregate my predictions and combine it together to form a combined decision. Okay, so that's overview of ensembling model. Okay, so it's simply put, sometimes people will be wondering, okay, so in order to, train a very good model, I have to choose the best tip for ensembling. In this case, you can see for model one, I'm using a best model. Here I'm using best model, like that. It's not like that. Sometimes even weak models can do a good job, where you can see, like, some tasks cannot be done using CPU, but those tasks can be easily done using a GPU, right? Because GPU doesn't have bigger cores, but it has more number of cores, which will help to handle the graphics very simply and easily, whereas your normal CPU cannot handle that. So that's the beauty of GPU. Likewise, even weaker models can do a good job if they're assembled together. What I'm trying to infer is, like, sometimes I don't even want the best model into action. I can certainly, or I can possibly use weaker models as well to do the job. I'll just, give a very simple idea about ensemble. As I told you, I try to, create multiple models for the given data and try to predict it, or it can be used for, classification, and even can be used for regression. Okay, regression is going to be numbers. Okay, so whatever number which I get, I try to get an average or a mean, or, some statistical notation from the entire data collectively, and I can able to present it. Or if it is a class, I can, I can combinedly see, like, how many predicted class A and how many are predicted class B. Based on that, I can take a decision. Sometimes people even go with the weaker model. Okay, so instead of going with a better model, a bigger model into concepts, sometimes bigger model can be too much of complexity, can add too much of complexity to the model training. So people even go for the weaker model, so that the inferencing will not be too much time taken. And there are commonly used techniques for this ensembling. One is bagging, and another is boosting. Okay, so overall, a broader perspective which I can give to this ensembling technique is either using bagging method, which we can also call it as bootstrapping, or we can also say, we can also, go with another strategy known as boosting. Okay, so as in the name, you can see bagging utilize bigger models. Okay, and boosting utilizes smaller models. Okay, that's the contrary between this bagging and boosting. So you can see bagging utilizes a complex model and try to smooth out their prediction, because, complex model will have good predictions. So overall, it will have, like, all the model will have a prediction accuracy of 75 to 85. So using this aggregation, it will try to, balance out the prediction even more smoother. But this weaker model, boosting technique utilizes weaker model that will give, that will give its learning to the next model. So each and every model will be connected together. It's not like only the output is connected. Here, the learning itself will be connected. So that's the difference between boosting and bagging. So bagging, model learns separately. It tries to, predicts, combine the predictions together, and you get an output. Whereas boosting, all the model will be jointly learned. Okay, it will jointly learn, and it will try to create a predictions out of it. Okay, that's what we called as boosting. Okay, so we'll deep dive into these two contents. Okay, so first let's understand what is bagging. So as the name implies, okay, bagging. Okay, so bagging is something like, you're trying to bag up the data. So you can see you have different data here. What I'm trying to do here is, from this original data, I'm going to take some 70% of random data and give to this particular model. Okay, let's say this is your support vector machine. Okay, with RBF kernel. Okay, and let's say this is 70% random data. And again, I'm taking another 70% of data, which is again totally random, which is not totally, same as this guy. And I'm using support vector machine again, but this time I'm going to use a linear kernel. And third time, I'm again, like, multiple times, I'm using different 70% of data, which is randomly taken. And I'm using different support vector machine with different hyperparameters. Let's say C is equal to 0.1, 1, 2, 3, and even sometimes kernel can be polynomial or something like that. Okay. So likewise, I will be, playing only with my what is that like? I can play with my data and I can also play with my model as well. Sometimes people keep things very simple. Okay. Sometimes what they do is they only play with the data alone. Okay. Which means that like they kind of, distribute the data differently for different models, but every model will be the same, which means that like it will be having support vector machine with default settings or, with RBF kernel for all over, which means like all the models, parameters and everything will be the same. Only the data is going to be a little different. But obviously, with just the data, the model performance can vary. This model can have, 60% accuracy. This can have 70%. This can have 75 or 65, something like that. So, which means that because of the variation in the data which I create, the model will be totally different. It's not like, sorry, it's not like all the model will be learning similarly. It's not like that, because you are going to like, hide few data which is not seen by this model 1, but seen by model 2 and model 3. And you might have some data which is only seen by model 1, but not by model 2 and model 3. So likewise, people utilize different strategies. This is one strategy. Okay. Utilizing different data. Sometimes people use different models. Let's say support vector machine, decision trees, random forest, Gaussian naive, different models with the same data. Obviously, like, the evolvement is going to be totally different, because each and every model will have its own algorithm to learn. So obviously that's also going to be, that's the second strategy. Third would be like, changing the data and changing the model as well. Okay. Both will be changed, which will be even more random. That's also, another way of doing it. This is, three common strategies which people use in terms of bagging. Okay. And there's one more catch to it. Okay. So once you get the classification output, let's say this, this model creates, classified as class B, class A, and this is also saying it as class A, and this is saying it as class B. So obviously, when I combine all these decision, I'll be ending up saying it as class A, correct? Because most number of people have said, as most number of models have chosen class A, which means that class B is not good, is not the right one. So this is one way of doing it. But sometimes you also take the confidence into consideration, okay? Because each and every model will have its own confidence. Okay, let's say this model has a confidence value of 0.1. Okay, and this guy has a confidence value of 0.2. And this guy has a confidence value of 0.7. Which means that even though I aggregate these two guys, I'll be having for class A, the overall confidence is going to be 0.3. And for class B, I have an overall confidence 0.7. I can also do a favor of, getting the output to be class B based on the confidence value as well. The bigger the confidence value, that will be given. Even though only one classifier have said it has class B, but it is more confident than these guys, then definitely I'll be choosing class B. So there are different strategies. That's what I say. Like, bagging is a technique where you can, try different methodologies. Say, like I said, told you, like, you can use different weighting strategies after the prediction or before the prediction. You can change the model, you can change the data, you can play with all these things. Okay. This is what we call it as bagging. Okay. Is this clear? Any doubts or clarification at this point? Okay. So since there are no doubts, let's go for this next concept known as boosting. Okay. So boosting again has two different methodologies. Okay. Two broad methodologies, I would say. One is ADA boosting, another one is gradient boosting. ADA boosting can also be, can be told as adaptive boosting, and gradient boosting can also be termed as grad boosting or something like that. So basically, boosting has two more broad categories inside it. Let's see like how it works. Let's go to ADA boosting first. Okay. So what the ADA boosting does, as I told you before, bagging as a possibility that it can go with the complex models, correct? Bagging will try to see whether it can go with the complex model, whereas boosting will mostly use, simpler model, which means that, like, it's going to go with a very, very simple model. Okay. So how does it work? So basically what it happens, okay, I'll just give you a very, a very simpler overview of this, and then we can deep dive into this ADA boosting. So basically I will be giving this entire data to the model. Okay. The model is going to be very, very simple. Okay. So it's going to be like very simple in nature. Okay. So it's trying to, train, and it tries to classify. During the time of classification, okay, these many data has been wrongly classified. Only this 6 data has been correctly classified by the model with the simpler model. Let's say only 20% has been classified correctly, and 80% has not been classified correctly, which means that in the next iteration, okay, in the next iteration, this will be penalized more, asking my newer, weaker model, the next model which is about to learn, I'm going to say prioritize on these data. Okay, leave these guys because I've done a good job. The initial guy have done a good job. Let's not mind about this guy. Let me, let you focus on the data which this classifier one didn't do. So in this case, you can see all the data which you see is based on the wrong prediction. So now in this case, I might be getting some good predictions, and again I'll be losing more data because obviously like this is also a simpler model. Likewise, it will go iteratively again and again and again to make sure all the wrongly classified data has been classified by any of the models at least. Okay, for example, if there are 10 models here, and you have 100 data, each and every model would have classified 10 data correctly. Okay, so and maybe 90 data wrongly. So when I like divide this 9 data again, some model would have predicted 10 out of this 90, 10 would have been predicted by some one model, another 10 would have been predicted by another model, another 10 would have been predicted by another. Likewise, all the wrongly predicted data would have been predicted correctly by at least either one of the models. Okay, so that is how this boosting works. So it's kind of giving a feedback, okay, where which data have to be emphasized more than going just like that. Because even though you can see the model is very simple, which means that it's going to have a very, very simple model. Let's say a decision tree with only one branch, which means like, it have only one decision to make. So it's a very simple model. Likewise, I can go with a very simpler model and I can, boost my, next upcoming models with the learnability or with the experience which I gain from the different models. Okay, so this is known as adaptive boosting, which is like adaptive in nature. Similarly, okay, very similarly to adaptive boosting, gradient boosting will also work. The only thing is like, instead of giving the penalty of wrongly predicted one, I'll be pushing it in terms of a gradient, okay, in terms of an error rate or your loss function. Okay, so we'll talk about this loss function even more very clearly when we go into neural networks. But in this case, as you saw in the support vector machines, right? So more the soft losses are, more fluctuation the model will have, and will try to reduce that loss as much as it can. Similarly, like every small module which has been trained will have some error rate. So that error will be like passed as a gradient, like similar to a gradient descendant which you see in neural network, which will be very similar to that, and it tries to pass this error rate towards different weaker models and make it perform really good. And one more thing is like, it's not like the final model will be used for prediction. Okay, it's not like that. All the models will be used for prediction, because ensemble is a technique where all the predictions has been taken into consideration, which means that the flaw of this model 1 would have been taken care of this model 2. The flaw of this model 2 would have been taken care of this model by this model 3. The flaw of this model 3 would have been taken care of by this model 4. Likewise, each and every model will adapt to the flaw which has been taken to the previous model. Okay, so this is what ADA boosting and gradient boosting will do. Basically, it learns, it boosts the models, upcoming models based on the weakness it has been created. Okay, now let's deep dive a little bit more into boosting. Okay, this is an example which I'm trying to create here. Okay, so let's take this as a data. Plus is one class and minus is another class. Okay, so what I'm trying to do now is I'm trying to train different models here. Okay, let's take this first model. Yeah, so I'm just trying to draw a decision like this. Okay, let's take my support vector machine is drawing this line, something like this. This is model 1. Okay, and model 1 has predicted, trying to predict, classify this class A and class B. And in this case, you can see what happens. This has predicted correctly. This is very good because left side it has only plus, but in the right side, 2 things have been wrongly predicted. Correct? This 2 data has been wrongly predicted. Now, what I will do is I will pass on this learning to my model 2. Now, this model 2, what it does, it will prioritize for these 2 data. It doesn't care about these data. It will prioritize only for this data alone, which means that it's going to draw a line, something like this. Now, in this case, these 2 higher priority data has been like, somehow taken care of by this model 2, but again, it has two different data, and this data is also not being taken care, which means that out of these two, at least this data has been taken care by this guy, which means that this is a new flaw which has been found in this model too, which means that the next model, this learnability will be given, and I'll be trying to draw a line, something like this. So in this case, this data has been prioritized more, and again I'll be having two more data. Likewise, in this case, what I will do, I'll try to draw a line, something like this. Likewise, every model will try to prioritize the shortcomings which has been covered in the previous model and try to do. So now every model, when it combines, for example, let me take this as my data. Okay, this is my input data. Now let's see like how the model performs. So this is my query data. So this model will say it as class B, correct? This model will say it as class B. That's also correct. But this will say it as class A, and this will say it as class B, correct? So the majorities belongs to class B. Now let's take, let maybe this data. Okay. So for this case, this will say it as class A. For this, it will say it as class B. This will be seen as class A, and this will be said as class A. So something like that. So likewise, I can, go with multiple boostings, multiple small models. At some point in time, you can see each and every weaker model has been, those shortcomings or those flaws have been covered by the upcoming models. Even though that is even weak, that doesn't matter, because the flaws has been taken care, iteratively and slowly at a boosted manner. Okay, this is what we call it as boosting. Is this clear? Any doubts or clarifications? This is a simple idea which I'm trying to give. Okay, so it's not like this is how it works, because there are different strategies where the model level. This is like based on support vector machine, which I'm trying to say. The boundaries are being drawn. If you're using a different model, maybe the strategy would have been a little different. But basically, this is how my model evolved. Instead of me trying to draw one single perfect line, something like this. Okay, yes, this can also be done. It's not that tough, but let's say when I get some plus value here, my model will fail, correct? But with my previous learning, okay, so with my previous learning, I would say the model has evolved really great, and I might be like having something like this. In this case, is plus. When I have this plus here, this will be class B, this will be class B, and this will be class A, and this will also be class. So I'll have a 50-50 prediction here. Whereas in this case, when I use this one, I'll be wrongly predicting it as class B, which is wrong. So something like that. Okay, so instead of using a singular complex model, I can also go with the multiple weak models also. Yep, this is attendance link. Okay, the attendance is given. Attendance link is also given. But yeah, so this is all about boosting. Okay, yes, you can very well utilize this strategy, for your data. It's not like you have to only use boosting always. You can always use backing as well, because sometimes backing will also work pretty well, conveniently well. But many cases, people have created multiple different boosting techniques. Okay, there are multiple different boosting techniques which has been created, which creates a better model than a simpler support vector machine or logistic regression or something like that. That's one key takeaway which you can keep in mind. Yes, so the attendance link is already given. Oh, okay, they will share you the right link. Yeah, please don't worry about that. So the next concept, okay, so next the final concept which I would say is the random forest. Random forest is also another useful technique which is based out of backing, but it kind of have different strategies to it. What it utilizes are, it uses backing technique where the training set is kind of sampled with different random percentage or random probability of 50% or 70% or 60%, and then it use lesser feature for subset, which means that, for example, if you have 10 features or let's say 10 columns of data, I'll be giving only 7 columns for this guy. And I'll be giving some 8 columns, some random 8 columns for this data. Likewise, I'll also reduce the feature set, and I'll be making sure the decision trees which I'm creating is very small, which is limited to, 1 or 2 branches. Okay. Basically, random forest is a collection of decision trees. Okay, it's based out of decision trees. Actually, it utilizes only decision tree as its you know as its model, inner model. But this model will have some limitation, as let's say it will only go with branch of one or two. To the maximum, it will have two branches, and you will have a it will be using bagging concept. But one, not only the data, it will also reduce the feature as well with different models which has been provided. So and finally, you will be creating a weighted voting average, and you get the prediction. And it is proven that random forest works little better than the decision trees, and and many different models as well. So because it is kind of utilizing this bagging technique, but in a limited way, where the model evolves really better than normal bagging technique. Because I'm not using any complex models, I'm using a very very simpler model to train with. Okay, but one more thing, one more catch to it is like, whenever you use ensembling technique, okay, ensembling technique are very useful when your time is not of a concern, which means that, for example, you are trying to chat with you are trying to ask for a question with in chat gpt. What if the chat gpt takes 1 hour to process your data? You will never use that, right? Because you don't want to wait for 1 hour. You'll try google, you try to solve the problem just like that by your own in that 1 hour time. So but sometimes you might be requiring a very good accuracy. For example, some brain tumor analysis, you should not be giving a wrong result. Even though it takes more time, that's fine, people can wait. Okay, because it's not going to be like harmful just in 1 hour. Even if it takes 1 hour, that's fine for me, because I have to get the right result. But if I get the wrong result, that's going to be a very big problem. But in terms of time sensitive data like ChatGPT or face unlock system or something like that, your model should be very very fast, which means that the inference time which which is there should be very very fast. Which means that when you have simpler and single models, your model performance, in terms of speed, would be like very good, because you have very lesser models. But when you go with bigger models and you have n number of models, like let's say 10 models, means definitely the inference time will increase. Inference time will increase, and it will take more time to produce results. Okay, they should be always a trade-off between speed and accuracy. Okay, so it's always like that, because sometimes an application requires speed more than the accuracy. Because let's say ChatGPT, sometimes it can make mistakes, but that's fine, but it gives you an instant, a swift response. But sometimes you might require an accurate result irrespective of the time. In some cases of some kind of forensic analysis or something like that, in that case, time is not a concern to me. I'll be like sticking with the accuracy of medicine. So whenever you require more accuracy and you don't care about the time, then you can very well go for this ensembling technique. Okay, ensembling technique is designed for creating, for accommodating more complex models. More the models will be there, better the ensembling will become. So obviously, more the model, more the complexity, and more the clock cycle will be taken. Which means that for non-time sensitive problems, ensembling will be very useful. For time sensitive problem, ensembling is not a good choice. Even though it gives you a better accuracy, I can stay with different model that is having less accuracy, but giving me better results. Okay. Okay. Okay, sorry. So my voice is now clear or more audible now. Okay, so sorry for that. I just moved away from my mic. So anyways, I'll just show you like how to run programs for this random forest and for this ensembling technique now. Okay, so let's see like how to train a model with bagging technique. So let me go for this bagging technique. So bagging, we have a function named bagging classifier. Okay, we have a function in bagging classifier. I'm going to use a classifier. Everything is going to be the same, guys. Okay, so there is no difference at all. Okay, the only thing is like I'm going to add few more lines here where I'm trying to train my model and see like how much time does it take. Everything is going to be the same. There's no big differences at all. Okay, so the previous code and the current code is exactly the same. The only difference which I made is here: bagging classifier and estimator, random state. Okay, so inside this bagging classifier, I have two techniques here. Okay, one is I can go with n number of estimators. What is estimator? In this case, I'm using 50 random models. 50 models will be created which means that, like, I'll be having 50 models that is going to have a different data data set to it. Okay, differently distributed data towards it. Okay, that's one thing. And the one more thing which we can do is, I can also create a model first. Okay, for example, in this case, you can see I'm creating a decision tree classifier first, and I'm taking this model, okay, and using this as a base estimator, which means that whatever 50 estimator which I'm going to create is going to keep the base, base branches as this base estimator, which the model has been evolved already. From this, the model will start to evolve, because sometimes you can use a matured model as a pre-trained, base model, and then evolve from there also. And sometimes you can also go with, something like this. You can see, like, I can very well go with the randomly initiated data as well. Okay, let's see like how it works. Okay, first thing is, like, I'm just loading the data, splitting the data into input and output, and then I'm just splitting the data furthermore into training and testing. First thing is, like, I'm just going to use decision tree and trainer model first, and I'm going to print the accuracy here. Okay, and I'm also give you the training and testing accuracy also. I'm going to print the classification report for the decision trees, and I'm going to use my bagging classifier without any base estimator. It's going to be like, randomly established estimators, 50 different estimators, and I'm going to train that model, and I'm also going to print the time, and I'm also print the training and testing accuracy and the classification report, something like that. Okay, so I guess this might not be required for now. Okay, let it be. Okay, I don't mind. Let's try to run this bagging program, bag.py. Let's see like how better the model is. So here you can see this is the, yeah. So this is for decision tree, and you can clearly see like I'm getting 71%, and this is for bagging. I'm also getting 71%. Where you can clearly see here, okay, so even though both are 71, okay, this is more balanced. In this case, it is more aligned towards class 0, but in this case, it's kind of balanced. Both has, at least like this is becoming 62, here it is 55. It's very, even more, very less. So I would say I would prefer this guy because it has a balanced accuracy for both the classes. Okay, this is one thing. And I can also, as I told you, I can also utilize the base estimator as the previous model. So I'm going to evolve from this particular model. I'm going to evolve from this particular matrix, and I'm going to utilize a bagging technique on top of that. Let me run this. Let's see like what really happens now. Oh, okay. I kind of know this. Yeah. Yeah. Now let's see the results. Now you can clearly see, since I'm using this base model for my bagging, okay, the model as aligned towards this guy, because it is creating more insights on this guy, because it is already leaned towards class 0 and not to class 1. So which means that sometime when you have this kind of imbalance problem, using a base classifier is not really a good good strategy, because you can see wherever the model is leaned, only that direction the model will grow. You can see very well from 49 it has become 48, and from 84 it become 86, which means that, like, the model is leaning towards class 0 again, but reducing this class 1's performance again and again and again. So that's one more problem which you can see when you use bagging with the base model, which has already evolved very badly. Okay. Okay, so this is all about bagging, guys. Okay, and you can very well see the time taken for bagging and time taken for training a model with decision tree. You can see for decision tree it is taking very less seconds, like 0.9 milliseconds, but for bagging it is taking like 74 milliseconds actually. So it obviously, because since you have more models to train, it will take some more time. Now let's try to run boosting technique. Okay, so I'll just go with this Zada boost first. Let's see like how this Zada boost works. And as I told you, like, again, everything is going to be the same, guys. Okay, so there will be like no difference at all. Similar to bagging, I can also have, I can also choose my base estimator also, whether it has to be randomly initialized or initialized with the pre-trained model, which has been evolved with the given data. So I do also have a, I can choose between these two guys. For now, I'm gonna stick with the randomly initiated 50 estimators, and I'm gonna compare against my decision tree against this Ada boosting classifier. Okay, so let's see like how it comes. Let me run for this Ada boost. Yep. You can see like the model is slightly better, not that great, but I would say it is like, again, it's better balanced in both the cases. Both the cases have, done a decent job. So I would stick with the 72. But what if I use the base estimator as my decision tree? Again, the linearity, the lineage will be towards the class one. Oh, sorry, the class zero. But let's see like how it evolves. Now you can see, since I've leaned too much towards class zero, the entire model got collapsed. So that's what. So in boosting, because error rate is very important to me. So since my model is already leaning towards class zero, the error rate can be like ambiguous. So because of this ambiguous error rate, my model is kind of collapsing here. So I would encourage not using any base estimator unless it's giving you a very decent result. Sometimes you'll be getting 80% of accuracy for both class A and class B. In that case, you can use a base estimator as that particular model, and you can evolve from there using AdaBoost classifier or something like that. But it's not a better better practice when your model is not doing a really good job and you're utilizing that as a base estimator. That will never work out. You can clearly see like the accuracy is like just 68%, which is falling down from 71. Similar to that, we also have gradient boosting, which is also very similar to your ADA boosting. So everything is just one single liner change. You can see like everything is the same. There's no big difference at all. The only thing which I'm trying to change is the function itself. Okay. So I'm using this function gradient boost classifier. I'm giving the hyperparameters just like that. That's all. Now let me run grad boost. You can see, surprisingly, gradient boost is even better, right? Because you can see like class B is also somehow taken care. Class A have been boosted even better. So I would say that class gradient boosting works a little better than adaptive boosting in many ways, because the gradients have been given and not the actual data. Sometimes pointing towards the data can be good, but when you have too much of distribution, pointing towards the data might not be doing a good job. In that case, I have to go with more estimators or something like that. And one more thing, you can see the training accuracy is like 100% for your decision tree, which I've used here. Okay. The decision tree which I've used here without any depths, which means that it might have more depths. Clearly it has overfitted here, correct? When I use this overfitted data, it's not going to create a good output. But in this case, you can see even though it is overfitted a little bit, but it is not too much overfitted with when compared to the decision tree. That's one more advantage of using it. So you can see like every model has been overfitted, right? So you can see ADA boosting is overfitted, and yeah, it is fine because since I didn't use a base estimator as a particular guy. Now let me do the same trick here. Use a base estimator of that overfitted guy. Let's see like how this evolves. Obviously, this will not be evolving really good, but let's see. Okay, so this doesn't have base estimator. Sorry, yeah. Gradient boosting will not have this base estimator. Okay, so only ADA boosting and bagging have this functionality, but gradient boosting doesn't have this functionality. Sorry, I forgot that. Okay, this is one methodology. And finally, we can also use this random forest. Okay, random forest is also an ensembling technique, and you can see the in the random forest, I can also give the n estimator, and everything can be the same. The only advantage of this random forest is like I can also control the decision trees. Okay, the number of decision trees which I want to create can also be considered, because in this case I can see I use the criterion to be Gini, impurity, and the max depth is 3. So it's kind of fixated. I can also reduce the depths. I can also play with these hyperparameters so that I can able to train the best model out of it. Now let me run this particular random forest and see like how better it is than the entire different techniques which were implied in this day. Let's see like how it works. Okay, clearly, right? Clearly, random forest have got a superior accuracy of 77%, which has not been achieved by support vector machine, or by your decision trees, or your or your bagging techniques, or your boosting techniques. All these techniques have been failed, but random forest proven to be little better than every guys, because you can see that we are getting like 77% of accuracy, even though the values doesn't seem little balanced. But I would say like the recall is a profound. We have got a profound value of 89 recall, which is really good. And all the person have reached almost like 75%. Only bad call is like this particular class one is not doing a good job. So what if I kind of reduce this, depth to 2, and let me run it. Because you can see the model doesn't overfit at all. It kind of, maintains or stagnant between 79 and the testing accuracy is 77. So always the training and testing accuracy should be, close by. If it is close by, it's not overfitted. If it is too much of a difference, then it is kind of overfitting or underfitting. Okay. So now I reduce the decision tree size, but again, it is not giving me a good result. But even though it is giving me a bad result, it is even more better. I mean, at least better than the other models which you have, saw. Likewise, I can play with this max depth as 4. I can play with this all day long to see, like, which gives me the best results. So based on, I can choose the best hyperparameter. I can freeze the model. Okay. So, yes, I can share you that. It won't be a problem. I'll just distribute to the coordinators and they will share to you. And yeah, so these are the, these are the strategies which you can bring. So what I would ask you is, like, try to utilize a data set. Okay. Try to, load a data set, possibly a numerical data set. Okay. And try to evolve that numerical data set and try to train these kind of different models. Okay. So let's say use decision trees, random forest, or bagging, add a boost, gradient boost. There are different techniques, different classifier which is available in your scikit-learn. You can very well, go to this particular website and try with different models. See, like, whether you can get some better accuracy. Okay. And also you can very well get this, data set by just typing PIMA Indian diabetes data set. Okay. So it's like the first link in Kaggle. You'll be getting that. You can very well download that particular, a CSV file, and you can try doing it just like that on your own. Okay. So let's see, like, whether you can able to, beat this result. Like 77 is the maximum reference score we have got. Okay. Overall, let's see, like, whether it can be, bettered by using your different techniques. But make sure the testing percentage is very important, because you should not be like using, the training set as your metrics. So I'm using 25% for my testing, which means that you should also be using the same 25%, and the random share to be 42. Utilize these two lines should be very important. Okay. This should have been matched by whatever, and rest of things you can change. Any any hyperparameters you can change. You can see, like, which is giving you best results. Do let me know. So tomorrow we'll see, like, who have got or who have reached better accuracy than this guy, like this random forest 77. Let's see, like, what can be done. So this is all about today's session. Do we have any doubts or clarification at this point? Any other gaps which you want to fill? Any conceptually you have any problems in understanding this random forest, boosting, bagging, your support vector machines, various techniques which is involved inside support vector machines, hard margin, soft margin? So all these things are there. So if you have any doubts or clarifications, now is the time we can clarify it. So yeah, the attendance forms is also there. So you can very well utilize that form. Okay, so I'll just show you this bagging one last time. So basically, bagging is something like, I'll just give you a very simple ideology. Okay, you have 10 data with you, or I'll just give you a very simple example. Okay, so bagging, I have 10 data with me. So in that I have 3 red balls. Okay, and 3 blue balls, 3 green balls, and 1 white ball. Okay, so when I train my model, I'm gonna consider 3 models: model 1, model 2, and model 3. What I'm gonna do is I'm gonna take 2 red balls and 1 blue ball and 1 green ball, which is like 5 balls have been taken, and that data alone has been given to this model 1. Now this model 1 will have more knowledge about this red ball and lesser knowledge about this blue and green, no knowledge about this white ball. Likewise, next time, for the next model, I'll take 2 blue balls and one red ball and one green ball. Again, similarly, I'm going to give like, five balls here. Now this model will, gain more knowledge about this blue ball, but red and green and white will not be more considered. Likewise, I'm going to like, distribute different data to different models. You can see like this model, all these models have the same architecture, the support vector machine architecture. The model is the same, only the data distribution is different. So when I train this model parallelly, each and every model will evolve differently, right? So obviously when I get the results, obviously this will give me different result, and this will give me different result, and this will give me different results. So when I aggregate these results together, I get the right output. So that's called backing. Whereas boosting, it is a little different. So instead of parallel training, it is like boosted among the models. Let's take this example. In this example, few have been detected correctly by this model, but few have not been detected correctly. This not detected would be prioritized by the next model. Okay, so the next model will try to classify the non-detected images or non-detected data by the class one, sorry, by the model one. So model 2 will try to overcome the flaws which is noted in model 1. Similarly, the model 3 will try to overcome the flaws which is not covered by this model 2 and model 1. Likewise, every model will try to somehow cover the flaws of these different models and come out evolve from them. So in that case, boosting will work little better than the bagging process, because bagging is particularly you are hiding the data, that's all. But in this case, you are boosting the learning methodology differently. But in this case, you're using a very weak model, not a very complex model as you use in bagging technique. Okay, so is this clear? Any clarification which you want to get? So maybe if you are a little confused, like search, try to see the video again. You might understand a little bit more about it. If you are even confused more, we can talk about this confusion tomorrow as well. Okay, so since the time is of the essence, we can I guess we can wind up for today. Okay, so if you are still confused, do let me know. Tomorrow we'll have a fresh round of discussion to understand more about it. Yeah, thank you everyone. Thanks for your time.
Hi, Deepan.
Yeah, yes.
Yeah,
Yes, no.
session is over now.
Yeah, yes, it is done.
Okay, you can leave the session. Okay. Yeah, attendance link is posted in chat. Okay. Please fill the attendance and feedback.